So now we would continue with the second place of our challenge, which is given by Yuchen with the title A Real-Time Fusion Framework for Long-Term Visual Localization. Yuchen Yang is joining us virtually on Zoom, and he will give the talk.
Hi everyone. My name is Yuchen Yang. It's my pleasure to introduce our work, Real-Time Fusion Framework for Long-Term Visual Localization. Our team are from Oppo Research Institute. In structure-based visual localization, a point cloud is needed. Usually, we use database images and given 6-stop poses to build this map. Mapping stage includes feature extraction, co-visibility, calculation, feature matching, triangulation, and bundle adjustment. In the localization stage, we still extract local and global features from query images. Global features are used for image retrieval, and local features are used in feature matching with retrieved database images. After that, PMP calculates the 6-stop pose of query image in point cloud map coordinate. This is conventional hierarchical visual localization pipeline. However, there are several challenges in visual localization. Firstly, seasons and illumination changes makes it difficult for image retrieval and local feature matching. Secondly, feature point matching fails in vegetation and low feature scenes, such as trees, bushes, and white wall. Thirdly, dynamic objects, scenes changes, and similar scenes makes it difficult for distinguished scenes, even for human beings. Also, in some datasets, database and query trajectories are not 100% overlapped. So that is impossible for one-frame visual localization to localize in locations that database not covering. To solve these challenges, we propose a fusion framework that fuses VIO and one-frame visual localization to achieve robust and accurate global localization in challenging scenes. The framework is divided into two parts, the local client and cloud server. On local client, VIO provides relative pose between sequential frames. Fusion part combines VIO and visual localization to produce final 6-stop poses. And on the cloud server, offline mapping outputs a prior map for visual localization service. Visual localization service utilizes prior pose and images from local client to calculate global pose in mapping coordinate. We choose a light-weighted HFNet to achieve real-time localization. The details of each part will be discussed in the following pages. And in this challenge, we modified local and global descriptor and matching method in visual localization to achieve higher accuracy. We use NetVRAD as the image retrieval, and we use SuperPoint for local features. And we match features between images by superglue. And we calculate localization result offline and fuse it with VIO. In the following pages, we will still introduce our method using HFNet. In the offline mapping stage, given 6-stop poses are utilized to search co-visible frames. Then we follow CoMap pipeline, which include key point matching, triangulation, and bundle adjustment. We also employed observation constraints, which was proposed in our previous work. Finally, in point cloud map, each camera includes global descriptor, camera pose, normal vector, and observed point clouds. Each point cloud includes pixel coordinate, 3D position, observation cone, maximum observation distance, and local descriptor. In visual localization service, we use prior pose from Fusion to help image retrieval, which overcomes similar scenes such as tunnels and corridors. Parallel feature matching produce n poses from n candidates, and dbScan filters out incorrect poses. And after a pose refinement, a coarse pose is sent to observation constraint to retrieve more point clouds and refine the final pose. In image retrieval, for example, if we want to retrieve top K database candidates, we firstly retrieve 10K candidates and filter out database candidates whose pose is far from prior camera pose. And finally, we still keep K candidates according to retrieval rank. In observation constraints part, we firstly search co-visible database camera with coarse pose according to their position and the camera normal vector. Then, in the point clouds observed in these database cameras, each point cloud descriptor is only visible in a limited cone. And we select the point clouds whose observation cone covers the coarse pose. Finally, we perform feature matching between 2D features and retrieved point clouds and refine the output pose. And as we described before, on local client, VLO provides keyframe and frames to Fusion. Fusion sends keyframe images and Fusion pose to visual localization as a private pose. When visual localization service returns localization result, our Fusion needs a multi-frame initialization first to acquire stable initial pose. After that, we judge whether localization is valid and synchronize frame and keyframe sliding window. Dynamic weights are applied to visual localization edges in postgraph. And finally, postgraph outputs 6 stop poses of each frame. In initialization, we calculate transformations from VLO coordinate to visual localization coordinate of each keyframe. We call it a drift measurement. Then we perform a k-means clustering to drift measurements and find a stable drift between two coordinates as the initial state of the fusion. In postgraph optimization, we maintain a local normal distribution of drift measurements to judge whether a new visual localization result jumps too far or not. We also compare differences of VL and VRS measurement of adjacent keyframes. Then we can acquire valid keyframes and put them into postgraph optimization. We propose a drift ransack to remove outliers in drifts and calculate dynamic weights of each visual localization edges. This is a demonstration on outdoor dataset, 4 seasons city loop. We use city loop to train as database images. And we can see that our framework achieves stable and accurate localization in cross-season scenes. Fusion solves vegetation and tunnel scenes, which are difficult for one-frame visual localization. We also tested our framework on indoor scenes. OpenLoris dataset covers several indoor scenes. It also includes scenes changes, dynamic objects, and illumination changes. And some of the sequences are partially overlapped. For example, in this sequence, home 1 and home 3, their trajectories are not 100% same. So our method combines VIO and visual localization and successfully solve this problem. That's all of my presentation. Thank you for your attention.
thanks a lot for the great talk. Are there any questions from the audience?
Hi, and thank you for the presentation. The question regarding the capacity of the map that you store. What is the size of the map that you store in the storage or in the dataset, in the database?
For example, when we use the city loop sequence, the total size of the map is about 5 GB, I think.
Okay, and the second question is what is the distance and how you adapt your method to large scale?
Sorry, I didn't
Like
understand the question.
How you adapt your method to large scale?
Maybe I can say a word on that. I mean, it depends on how you define large scale. I would say the scenarios you've been seeing are already can be considered as large scale. So some of the trajectories, for example, the city loop is around 10 kilometers. So it depends on how you define large scale, but it can be already considered as large scale if you're referring in this direction.
Yes. Okay. Thank you.
Okay.
Are there any other questions from the audience? If not, I would also have a question. I am interested in the choice of local descriptors and descriptor matching. So you've been mentioning you're relying on SuperPoint and SuperCLUE. Can you say a couple of words on how sensitive your method is on the choice of descriptors and matching?
Okay, we tested on HFNet and use KNN to do the feature matching, and we also test SuperPoint and SuperCLUE. And according to our test, SuperPoint and SuperCLUE solves the night scenes, and we use night images and to localize on a day map. But HFNet seems to fail in this scene. And but if we localize a day image on a day map, the difference is about several percentage of the accuracy. Yes.
Okay, thanks a lot. And maybe a small following up question. Have you considered any pre-processing towards the data as the other participant did to the raw data?
No, we just follow the whole map pipeline. We didn't use any semantic labels or other pre-processing.
Okay, thanks a lot. If there are no more questions, yeah, I would like to thank the speaker again, and we can move on with the schedule. Thanks a lot.
Thank you.